What are wormholes? Let's talk about it. Imagine you're floating in the depths of space when you encounter something extraordinary. At first glance, it looks like a black hole, a perfect sphere suspended in the cosmic void. But as you drift closer, you notice something is fundamentally wrong. This sphere isn't consuming light. It's revealing it. Through its surface, you don't see darkness. You see a view, clear, sharp, impossibly distant. The rings of Saturn. The spiral arms of a galaxy billions of light years away. Perhaps even a completely alien star system. For what you have found is not just a window in space. It is a window through space. If you were brave enough to cross this shimmering boundary, the transition would be seamless. One moment you're approaching what appears to be a hole in space. The next you emerge somewhere else entirely. Behind you, your original location now hangs in the distance as a glowing sphere, a portal home shrinking as you drift away. This is what physicists call a traversable wormhole, a shortcut through the fabric of spacetime itself. But are these cosmic tunnels real? Or are they mathematical curiosities dressed up as physical possibilities? To answer that, we have to rethink what space actually is. For most of human history, space was thought of as a stage, an unchanging backdrop. Flat, eternal, passive. Stars were born and died, planets orbited, galaxies collided, but the stage itself remained perfectly still. Even if you removed every particle of matter, something would remain. Empty space, stretching infinitely in all directions. Einstein shattered this picture. In general relativity, space and time are not separate entities. They are woven together into a single dynamic structure called spacetime. And this structure is not rigid. It bends. It stretches. It curves in response to matter and energy. Think of spacetime not as hardwood flooring, but as a soft mattress. Place a bowling ball on it and the surface depresses. Roll a marble nearby and it curves toward the bowling ball, not because of an invisible force pulling it, but because it is following the shape of the curved surface. That curvature is gravity. Planets do not orbit because they are pulled across empty space. They follow the curves of space-time itself. But once you accept that space-time can bend, a deeper question emerges. If it can bend, could it fold? Could distant regions of the universe touch? Einstein's equations say yes. In the mathematical landscape of general relativity, space-time is flexible enough to connect regions that would otherwise be unimaginably far apart. Imagine a flat sheet of paper. Two corners sit on opposite sides. An ant walking across the surface would need to cross the entire sheet to travel between them. But fold the sheet, and those distant corners now touch. If the ant could step through the fold, the journey would be almost instantaneous. That fold is the idea behind a wormhole. But the equations allow more than intuition suggests, and that's where things become dangerous. The first wormholes emerged not from science fiction, but from Einstein's own equations. In 1935, Einstein and Nathan Rosen discovered what we now call an Einstein-Rosen bridge. Their mathematics suggested something astonishing. Black holes might not be dead ends. If space-time curves enough to form a black hole, the curvature might continue, connecting to another region of space-time entirely. In this picture, a black hole becomes a tunnel. Matter falls in from one side. On the other side, a mirror structure, a white hole, expels matter outward. Two universes connected by a bridge. It is an extraordinary idea. There is only one problem. You cannot travel through it. Einstein-Rosen bridges collapse faster than anything can cross them. Even light cannot traverse the throat before it pinches shut. Fall into a black hole hoping to emerge elsewhere, and you will not become an explorer. You will become an ex-explorer. If wormholes are to be useful, if they are to function as cosmic shortcuts, they must be a different kind entirely. They must be bridgeable. The early universe may have briefly allowed what today seems impossible. In the first fraction of a second after the Big Bang, space-time was not smooth. It was violent. At quantum scales, far smaller than atoms, space-time behaved like a turbulent foam, constantly fluctuating, bubbling, tearing at itself. Some theories suggest tiny wormholes may have formed naturally in this chaos. Threaded through these microscopic tunnels could have been exotic structures known as cosmic strings. One-dimensional defects in space-time itself. As the universe underwent rapid inflation, these wormholes might have been stretched to enormous scales. In principle, one entrance could sit in our solar system, while its exit lies in a galaxy billions of light years away. From the outside, such an object might look almost identical to a black hole. The same spherical symmetry, the same gravitational lensing. The only clues would be subtle, unusual radiation patterns, or matter flowing in ways black holes cannot allow. It's speculative, but not forbidden by the equations. And if nature did not provide ready-made wormholes, there remains another possibility. We could try to build one. A traversable wormhole must satisfy several conditions. It must connect distant regions of space-time. It must lack an event horizon. It must be wide enough to avoid destructive tidal forces. And most critically, it must stay open. Gravity hates wormholes. Left alone, space-time pinches them shut instantly. To keep one open, you need gravity that pushes instead of pulls. You need negative energy density, a form of matter more radical than antimatter. Normal matter bends space-time inward. Exotic matter would bend it outward. It would create repulsive gravity. This is not entirely fantasy. Quantum mechanics tells us that empty space is not empty. It seethes with particle-antiparticle pairs that flicker in and out of existence. In laboratory experiments, through effects like the Casimir effect, we can manipulate quantum vacuum energy in ways that resemble negative pressure. The question is scale. Could these tiny quantum effects be amplified enough to stabilize a macroscopic wormhole? We do not know. But even if we could solve the engineering, a deeper problem remains. Wormholes do not just bend space, they threaten time. Because space and time are inseparable, connecting distant regions of space also connects distant moments in time. And here, relativity complicates everything. In Einstein's universe, simultaneity is not absolute. Different observers slice space-time into now differently, depending on their motion. If a wormhole connects two regions moving relative to one another, the time experienced at each mouth can drift apart. Now imagine traveling instantly through that wormhole. You could arrive before light from your departure point ever could. Under certain conditions, you could even return before you left. This creates what physicists call a closed time-like curve, a path through space-time that loops back on itself. cause and effect would collapse. You could send yourself a warning about a disaster that hasn't happened yet, preventing it, eliminating the reason for the warning, restoring the disaster. These are not philosophical curiosities. They represent a breakdown in the logical structure of space-time. Stephen Hawking proposed the chronology protection conjecture. The idea that the laws of physics conspire to prevent time travel and preserve causality. Perhaps exotic matter cannot exist in sufficient quantities. Perhaps quantum fluctuations would destabilize any wormhole the moment it forms. Perhaps the universe simply refuses to allow causal paradoxes. General relativity permits wormholes. But mathematics permits many universes. Nature is far stricter. So, are wormholes real? We don't know. They exist in the equations of general relativity. They are consistent with the mathematics. But we have never observed exotic matter. We have never found a stable passage through space-time. And we do not yet possess a complete theory of quantum gravity, the framework that would ultimately decide the issue. Wormholes may be impossible. Or they may be hidden, embedded quietly in the structure of space-time itself. The equations do not forbid them. The universe has not confirmed them. And that tension between what mathematics allows and what reality permits is where modern physics truly lives. The same equations that describe the fall of an apple also describe the possibility of tunnels through space-time. Whether those tunnels exist is not a matter of imagination. It is a question only the universe can answer. And until it does, wormholes remain suspended exactly where they belong, between the possible and the real.